Good morning, everyone, and welcome to really our last new lesson of the semester of the course. And it's kind of fitting that this last lesson pretty much brings us back to the beginning. If you think back to the beginning of all of this calculus stuff, we spent a lot of time working with things called limits because the limit was really that extra ingredient that we needed to add to all of our previous knowledge about mathematics to create calculus. The limit came into play when we developed this idea of the derivative or slope of a curve or slope of a tangent. The limit also came into play when we worked with the area under a curve, which of course is connected to integration. Now there's a lot more about each of those two things, but I think we have a pretty good understanding of how the limit fits into those two big branches of calculus. Our last topic is to revisit limits, and quite honestly, now that we know something about derivatives, we're hopefully going to get a more efficient way to find limits. And to start off, I want to look back at maybe three types of limits that we've studied so far. This first one, we have x squared minus 4 over x minus 2. We know that we have a problem whenever we try to use direct substitution, and the limit turns into be a 0 over 0, or what we call an indeterminate form. If I put a 2 in both of these, I get 0 over 0. I can't figure out what's happening. So here the simple thing to do was to simplify it or rewrite it, cancel, and we end up with a situation that we can just put a 2 in. We get x plus 2 on top. Once we reduce, put a 2 in, you're going to get 4 for an answer. This second one, we have the limit of sine x over x as x goes to 0. Again, putting the 0 in is going to lead to 0 divided by 0, an indeterminate form. This case, we didn't have an algebraic method to simplify it. So what we did by a series of approximations, we made a table. I think we even made a graph, and we realized that by this thing called the squeezing theorem, that this limit really is going to be 1. And then this final one, we have the limit as x goes to infinity. So we're talking about end behavior of a function. Again, we could do things algebraically, but there were some shortcuts here. The shortcut in this case was that because the numerator and denominator had the same degree, all of these other terms are really negligible. So we just look at the coefficients of those lead terms. So it's going to be 2/3. But today I want to take a look at a new rule, a new fact, a new theorem that will help us tackle these in a different way, but also others that these methods would not work. So let's take a look at this rule. It's known as L'Hopital's rule. And basically it's saying this, that if we have some limit of a quotient of two functions, and that limit turns out to be an indeterminate form. For now, we're just going to stick with 0 divided by 0. And that these functions are differentiable. I'll call it f of x over g of x because that's a little more common. These functions are differentiable, but we try to put the number in and we end up with 0 divided by 0, which again is an indeterminate form. The rule says that that limit is going to be the same as the limit as x goes to c of the derivative of the top function divided by the derivative of the bottom function. We're not using the quotient rule. We're actually taking the derivative of the top and bottom separately. So let's see how that would play out in these examples that we've already put on the board. In this first one, instead of doing the algebra, I could just realize that this is going to be equal to a new limit. Take the derivative of the top, we get 2x. Take the derivative of the bottom, we get 1. Now if we put a 2 in, because it doesn't lead to an indeterminate form, we get 2 times 2, which is 4. So we didn't have to perform the algebraic steps. Again, that's only going to be true when we have a 0 over 0. This other one, if we try to apply L'Hopital's rule, thinking of this as f of x and this is g of x, it will be the same as the limit as x goes to 0. The derivative of sine is cosine. The derivative of x is 1. So we now use direct substitution. The cosine of 0 is 1. We get our answer 1. So, anytime we have a 0 over 0 indeterminate form for a limit, instead of trying to do things algebraically and rewriting the original, we can just take the derivative of the top and the bottom separately, then try direct substitution and see what happens. If for some reason we take one step of L'Hopital's rule, we try to use direct substitution and it's still 0 divided by 0, we just apply L'Hopital's rule again, and we could apply it again and again. Let's look at the third one. In this case, we don't have 0 divided by 0. But there is another indeterminate form that's acceptable, and that's infinity divided by infinity. Remember, we call these indeterminate forms because we don't really know what's happening. There are rules that are contradicting themselves mathematically when we have 0 divided by 0. A number divided by 0, I could handle. It's undefined. 0 divided by a number, I could also handle. That was 0. Same thing with infinity over infinity. I have a function getting really large, divided by another function getting really large. We don't really know what's happening. So we can apply L'Hopital's rule equally as well with infinity over infinity. So let's apply it. Here, if I take the derivative of the top, it's going to be x going to infinity. The derivative would be 4x minus 6 over 6x. If I try to use direct substitution, we notice it's still going to be infinity over infinity. So I apply L'Hopital's rule again. Derivative of the top is 4. Derivative of the bottom is 6. We reduce it, we get 2/3. Remembering that any limit of a constant is itself. So there we have it. L'Hopital's rule as a way to evaluate limits that up to this point we could do using other methods, but here we have another option. Next, I want to take a look at a few situations where we would have been stuck without L'Hopital's rule. So here are a few more examples. Let's say we have the limit of e to the 2x plus 1 divided by x as x goes to 0. And I'm going to make this minus 1. So if we're faced with this limit, let's say on a worksheet, on a next test, or even in the exam in a couple of weeks, we try direct substitution. We put a 0 in, we're going to get e to the 0, which is 1, minus 1, all over 0. We get 0 over 0. Good, we're happy, because that's one of our indeterminate forms that we can now directly apply L'Hopital's rule. We apply it. We just state that the limit as x goes to 0. The derivative of e to the 2x minus 1 is going to be 2 times e to the 2x. The derivative of x is 1. Now we can try to go ahead and make direct substitution. We put a 0 in for x. That's e to the 0, which is 1. We get 2. So this indeterminate form turned out to be 2. And again, there's nothing algebraically that we could have done to rewrite this in order to make better sense of it. Now I know that we've been spending a lot of time lately on integration, and now we're moving back to some differentiation, so it would be a nice review also for the exam. Let's take a look at one more example. Limit as x goes to infinity, log x over x. Let's see what happens. As x goes to infinity, log x goes to infinity. So remember, the log function basically looks like this. It's going to keep increasing even as we move out in larger x values. X going to infinity, of course, that's a straight line. Now, sometimes intuition is kind of fun to play with. When I think of this, I know this is increasing. This is also increasing. But if I think of the visual, it seems that the bottom is getting bigger faster than the top. So my gut feeling is this bottom is so much larger than the top eventually that the quotient is going to go to 0. Now, if you don't share that intuition, that's fine, and sometimes intuition can backfire. So let's see what happens. We know it's a 0 over 0, infinity over infinity. It's always good to make sure it is one of these indeterminate forms. So let's apply L'Hopital's rule. The derivative of log x is 1 over x. The derivative of x is just 1. While using direct substitution, that's 1 over infinity. And that happens to be 0. So in this case, my intuition was good. But intuition is not mathematics. It might lead you down the path of getting to an answer, but we want to kind of reinforce and make sure that what we're thinking is true. So on the surface, L'Hopital's rule is a way to evaluate limits. The limits that we are evaluating are those that up until this point we would have had to either use other methods, algebraic methods, or we would have been stuck. And they all require that we have 0 divided by 0 or infinity divided by infinity to apply. Now, towards the end of this course, you probably realize that quite often the main idea of a topic doesn't seem that bad. But then there are examples that can get a lot more intricate and more complicated. Just a few minutes, I'll set up another video of maybe some more advanced situations that we can still use L'Hopital's rule. But for now, I think this would be a good start for the problem set from 5-6. Be right back.